The first lecture of this mini course on general relativity and the positive mass theorem. Today I'm going to start with just some basic ideas from general relativity and end with a discussion of the Schwarzschild metric. So the setting for this talk is going to be a four-dimensional manifold. And the reason for that is because we want to have 3 space dimensions and 1 time dimension, but we don't want a distinguished time coordinate, so therefore we think of our 4 coordinates as living on a 4-dimensional manifold. Much of what I say in this mini course will apply to higher dimensions, but I want to stick to 4 dimensions for most of the discussion. So on our 4-dimensional manifold, we are going to have a Lorentzian metric. So what is a Lorentzian metric? It's similar to a Riemannian metric in that it's an inner product at each point, but the difference is the signature of that product is minus plus 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 instead of being positive definite, as would be the case in Riemannian geometry. So what that means in practice is that at every tangent space, we can find a basis of tangent vectors that are orthogonal to each other with the property that one of them, E0 in this case, has g of E0 is -1, and the other EIs have g of EI is +1. Okay, so just a notation comment is that in this series of talks, I'll try to use a bold G for Lorentzian metrics, because later on we're also going to have some Riemannian metrics. I'd like to use just like a regular G for those. So the reason why we like this minus plus 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 signature is because just as Riemannian geometry is modeled on Euclidean geometry, our Lorentzian geometry is modeled on Minkowski geometry. So the Minkowski metric is given by it's just the trivial ds squared equals minus dt squared plus dx squared plus dy squared plus dz squared. Okay, and the reason why we do that is because, well, a precursor to general relativity is special relativity, which I don't want to say too much about, but special relativity is basically determined by Minkowski geometry. And so locally we know that physics behaves according to special relativity, in the absence of any kind of gravity or anything else. So because of that, we want to say when you look really close up that it looks like the situation we know to be true from special relativity. Okay, well, since there are different kinds of vectors in a tangent space here, we want to distinguish them. So a tangent vector of the spacetime n is called timelike if GVV is negative. It's null if GVV is 0. In either of those cases, we call them causal, for reasons I'll mention in a minute. And it's spacelike if GVV is positive. So spacelike positive G, that's the situation we're most used to. What now we have to include the possibility of timelike. So a timelike vector, for example, would be like the E0 that I had on the previous slide, right? The spacelike example to be like E1, E2, E3. So an example of a null vector would be something like E0 plus E1. It's not hard to see that if you plug that in, you'll get 0. Or E0 minus E1 would also work. Okay, so the physical significance of these distinctions is that massive objects can only trace out time-like curves, while massless ones will move along null curves. So we interpret objects moving along null curves as moving at the speed of light. So photons, for example, would move along these null curves. So more specifically, the curves that are traced out by sort of test particles, they'll actually be geodesic curves for objects moving under only the influence of gravity. So, I mean, right now we're interested in a theory of general relativity as a theory of gravity. The metric G can be thought of as being the gravitational field. It determines what the gravity is. So if you're influenced by that and nothing else, then you should follow a geodesic. So one quick remark is that, again, I expect that you're all familiar with geodesics in Riemannian geometry. It turns out that, the way that it's defined in Lorentzian geometry is no different. The exact same different definitions work. So, you still have a connection. You still have Christoffel symbols. Once you have a connection, you can define a geodesic. So a lot of things do not change, actually. So the null vectors will actually form a double cone. Okay, and that double cone, so there's vectors above it and below it, both of which are timelike. So that distinguishes the future from the past. So here's a little diagram. This diagram is a picture of the tangent space at any particular point. And there's one dimension suppressed. But if you look at that, then you can see that the cone itself, the double cone that you see there, is all the null vectors, and those null vectors separate the time-like ones from the space-like ones. So the time-like ones reside above and below the cone, and the space-like ones are on kind of like on the sides, outside on the sides of the cone. So there are two. So you can see that since the time-like vectors are kind of divided into two pieces, we can distinguish them. And so we distinguish one side as the future and one side as the past. Okay. So now we can define the space-time, which is, we're going to use this word all throughout this series of lectures. It's the Lorentzian form manifold that I just talked about, but we also want a consistent choice of a future direction for each tangent space. Okay. So it's a little bit like, it's a lot like an orientability condition, right? An orientability condition, right? You can always choose an orientation at every point, but you want to make sure it can be done consistently. And this is the same thing. At every point, there's definitely a choice of how you want to, which side of the cone you want to call the future. And if you can do that consistently, we call that a spacetime. So that's kind of seems very reasonable to want on physical grounds, that we can distinguish future from past. Okay, but we actually are going to want some stronger causality assumptions. It's a little bit tricky because, unlike in Riemannian geometry, many of the spacetimes that we study in general relativity are not geodesically complete. So in Riemannian geometry, okay, sometimes you're interested in purely local questions, right? You'll just be looking at a small open set. But whenever you're interested in global questions, right, most of the time you're interested in complete manifolds, or complete ones with boundary, right? You don't just want like random holes to appear in your geometry, right? Random missing points, incompleteness. And in some sense, that's also true in general relativity. But the problem is there are a lot of interesting spaces that actually do have sort of missing points, and we want to be able to discuss them. So one important concept here is a Cauchy hypersurface. So a hypersurface M of a spacetime N is called a Cauchy hypersurface if every inextendable causal curve in N must pass through M exactly once. Okay, so first let me say, what is inextendable? It's pretty much what it sounds like. It means that you have a causal curve, right? And there isn't another causal curve that properly includes it. Okay, so what is the significance of having this Cauchy surface? Well, what that means is that every point in the space-time, you can reach M either by going forward or backward in time. Remember, so going along causal curves, you should think of that as meaning, there are a lot of causal curves coming from every point, but any causal curve coming from out of a point should be thought of as moving forwards or backwards in time. Okay, so I mentioned what is the significance of the word causal? Well, those are things that can affect other things, because if everything moves along either time-like or null, right, that means nothing physical is moving in space-like directions, which means that if two things are only connected by a space-like curve, they cannot affect each other. Whereas two things connected by a causal curve, well, the one in the past can affect the one in the future. Okay, so passing through M at least once, that means that every point can reach M either by moving forward or backward in time, as I just said. But passing through M at most once has an even more obvious interpretation, which is that, well, if you could pass through more than once, well, then that would be bad for causality, because it would mean that you have a curve that is hitting M twice, which means that if you leave M, you can then come back to M, and M should be thought of, I guess, as like a snapshot in time. So things happening, more or less simultaneously, they're only separated from each other in space. So you don't want to be able to leave M and then come back to M. That's the idea of the significance of this Cauchy hypersurface. Okay. A spacetime that contains a Cauchy hypersurface is called globally hyperbolic. This is not the standard definition of globally hyperbolic, but it is equivalent to the standard definition. For our purposes, we prefer to think about the Cauchy hypersurface definition. Okay, so something that helps with the intuition a little is that one can prove that topologically, if you have a Cauchy hypersurface, then the spacetime is just a product over that hypersurface. So it's just I cross M for some open interval in the real numbers. So, in fact, if you look at it this way, then you can kind of understand what I meant about how what's potentially missing here in terms of lack of completeness is, well, the inextendable causal curves. The reason the inextendable causal curves, they kind of run into the boundary of I, right? So either sort of go too far in the future and run out of space. Okay, so if I is again like a bounded interval, then you would have that incompleteness. Okay, in a globally hyperbolic spacetime, you do have a property that is shared by Riemannian completeness, right? So in a Riemannian geometry, completeness allows you to connect arbitrary points by minimizing geodesics. Okay, so here you get a similar property for time-like curves. So if you have a future time-like curve connecting 2 points, then there has to be a length maximizing future time-like geodesic connecting them. So, okay, one little bit of weirdness from Lorentzian geometry is, right, that instead of length minimizing curves, we actually are looking at length maximizing curves. But otherwise, it's very similar to the theorem that we know that tells us that 2 points in a Riemannian manifold, if it's complete, can be joined by a minimizing geodesic. So here, basically, if you have 2 points that are related to each other by a time-like curve, then you can find a maximizing time-like geodesic. Okay, so I'll just say that that these concepts won't play a role in a lot of what's coming, but they do play a role in one sort of particular topic that we want to talk about later. So we'll come back to that, but this is a natural time to sort of mention this causality condition of global hyperbolicity. Okay, so now let's get back to some core ideas of some other core ideas of general relativity, and that's the Einstein field equations. Okay, so first I'll say what is the G. The G is known as the Einstein tensor. It is defined to be Ricci minus a half scalar times G. So here the R is the scalar curvature of G. So like Ricci, it's a symmetric 2 tensor. And as the significance, the reason why the Einstein tensor is so important is because it's divergence free. So that's a reason why this combination Ricci minus a half RG is very natural. So the Einstein field equations say that this Einstein tensor, which is a curvature tensor of the space-time metric G, has to be equal to 8 pi t. So what is t? T is the stress energy tensor, and it describes the distribution of energy momentum in the space-time. Okay, so it acts as a source term for the gravitational field G. Okay, so what we're used to thinking classical physics would be that, okay, if you have matter, then it's a source for gravity, right? I mean, matter is an attractive, attracts other objects under gravity. Okay, and so if you could think of this equation as a somewhat complicated analog of Newton's law of gravitation. So one version of Newton's law of gravitation it says that the Laplacian of the gravitational potential is equal to the mass density. So this should be thought of as kind of like a souped up version of that. On the right side, we have something that represents the matter content of the universe, and on the left side is an operator on G. So the right side is telling us what the G should be, or at least constraining it in some way. Okay, well, the one reason why is stress energy tensor, we can't just call it like a mass density. That would be nice, but we can't, because actually it's important also, like, you know, how this matter is moving, right? So actually that's why I say it's like the energy momentum of the sources rather than just the mass density of them. Okay, so typically T arises from matter fields, which themselves obey another set of field equations, and that other set of field equations will account for how those fields respond to the influence of gravity. So in a simple situation in classical gravity would just be, oh, well, you know, there's a mass density distribution and it's just fixed, right? And then so you solve for what the gravitational potential would be. But in, you know, the reality is messier, because those objects that are influencing gravity are themselves influenced by gravity. They're moving around, they're interacting, they're doing stuff. So so T is capturing all of that somehow, and it's given in terms of these matter fields, and those matter fields are also obeying some equations. Okay, so those equations essentially are a whole other set of equations that would be coupled to the Einstein field equations. So some examples of those matter fields would be something like the electromagnetic field, which carries energy momentum. Okay, but we're not going to talk about any particular matter fields in this series of talks, so that's a level of complication that we don't have to worry about too much. In fact, well, one case we will talk about a bit, I guess, is the vacuum case, and that's when T is identically 0. So that's a simple, basically that's empty space, right? There's nothing there. And in the vacuum case, if you take the trace, then you can see that that's equivalent to just saying that Ricci is 0. So vacuum metrics are basically Ricci flat ones. And so far from being trivial, the vacuum case is already mathematically rich. We're interested in basically Ricci flat space-time metrics. Okay. The Minkowski spacetime is the trivial example of vacuum spacetime. The Minkowski spacetime has vanishing curvature. I mentioned earlier that in Lorentzian geometry, the definitions for connections and geodesics are pretty much the same as in Riemannian. Same is true for curvature tensor, right? The way we define the Riemann curvature tensor, the Ricci tensor, the scalar curvature, it's all the same in Lorentzian geometry. There's no new complications there. Okay, well, what about a non-trivial example? So it's natural to search for spherically symmetric solutions of the vacuum Einstein equations. There are a couple perspectives on why this is natural, but I mean, one is that you have some rather complicated system of PDEs, and you want to find solutions. Well, in almost any situation, the first thing you'd try is look for solutions with a lot of symmetry, simply because those are the ones you can find. So mathematically, that's important, and solutions with symmetry tend to be very important. A really common example would be if you just look at Laplace's equation and you look at spherically symmetric solutions, that lets you find the fundamental solution of the Laplacian, which is of course very important. And for similar reasons, the Schwarzschild metric which is the solution we're about to discuss, also has some really central importance in the study of Einstein's equations. But physically, it's also very natural, because physically you imagine, okay, what's a simple physical situation you'd want to model? Well, what if you just have some, a planet or a star, which is very approximately is spherically symmetric, okay? Well, inside the star might be tricky to sort of solve or think about what the stress energy tensor is doing, but what's really clear is outside the star is vacuum, right? So solving for spherically symmetric solutions of the Einstein equations that are vacuum, that's like solving for, the exterior of a star or a planet, assuming there's nothing else in it. So it's an idealized situation. To make our task easier, we're also going to look for solutions that are independent of a time variable. So this would be like, a situation where you have a star or a planet that's just not moving, not changing. Again, that's a very special situation, but at least, again, it's a very natural situation to want to understand. Okay, so if something is spherically symmetric and independent of the time variable, then we must be able to write it in the following form. So our ansatz is that G takes the form of minus some function times dt squared plus some function times dr squared plus r squared d omega squared, where d omega represents the standard metric on the sphere. Okay. So but why is it n squared and v to the minus 1? Well, that's just because it turns out a little bit nicer if I use those choices. But basically, the important thing is just there's two unknown functions of r alone that we want to solve for, or hope to find examples where this solves the vacuum Einstein equations. Okay, so to do this, we're going to impose Ricci equals 0 and hope we can solve for positive functions n and v. Okay, so the actual steps of doing this, many of them are tedious, but I'm going to essentially outline the important steps or that can be used to do this. So if you just look at a constant t slice, right, we can look at, so now I'm going to use this unbolded G to be v of r to the minus 1, dr squared plus r squared d omega squared. That's the induced Riemannian metric on any constant t slice. And if you think about the structure of bold G is a warped product over G, over regular G. So if you are familiar with the formulas for the Ricci curvature of a warped product, then we can write out what it means for the Ricci curvature of bold G to be 0. And again, those formulas, while standard, again, a bit tedious to actually derive, but they are pretty well known. So if you just plug into those formulas, then what you'll see is that being bold G being Ricci flat is equivalent to the Hessian of n with respect to regular G being n times the Ricci curvature of G, and the scalar curvature of G being 0. Okay, so now we know we basically just need to solve these two equations. All right, so let's focus on the second one first. Let's look at the scalar curvature of G. So the scalar curvature of G, that just depends on this unknown function v. And once again, well, it's not written right now as a warped product, but you could rewrite it as a warped product. So if you rewrote G as a warped product, then you could find a formula for the scalar curvature of G in terms of v. So that's what I wrote here, using the formula for scalar curvature of this warped product. Or I say or otherwise, because actually I think there are other kind of like slick ways that you can do it, but that's not important. Is that the formula that you get for the scalar curvature of a metric G in this form is 2 over r squared times 1 minus v minus r dv dr. Now remember, we're interested in when the scalar curvature is 0. So we're going to solve for when the scalar curvature is 0. So thankfully, if we do that, then the 2 over r squared just cancels away. And then the v plus r dv dr, right, we can just kind of rewrite that as ddr of rv. Okay, so this is some straightforward ODE manipulation. And of course, from here, pretty easy to integrate that. RV is just going to be integrating the 1 gives you an r, and then there's an integration constant. So normally we'd say r plus c, but for convenience, I know it's more useful to actually write this as r minus 2m. And so m is just some at this point, it's just some integration constant, but I'll maybe we'll get to its significance a little later. Okay, so then obviously divide by r, and you get v of r is 1 minus 2m over r. So we've solved for v. In other words, every solution that looks like our ansatz has to have this function v. So the only thing left, now we have to solve for the n. Okay, so the n has to satisfy Hessian of n equals n times Ricci. That's what we saw before. So in particular, if you take the trace of that equation, well, the trace of the Hessian is the Laplacian. The trace of Ricci is scalar, and scalar we already said was 0. So this says the Laplacian of n is 0. So this is not a hard equation to solve, because remember, everything here is spherically symmetric. So it looks like Laplace of n, but really it's just an ODE again, right? So n is a function of r, and we have an explicit formula for g, right? We have explicit formula for g. So if you just do your standard formula for Laplace Beltrami operator, using the fact that n is radial, right? So you only have this term for the Laplacian, you get this formula, right? Square root of v over r squared ddr of r squared square root v dn dr equals 0. Okay, and then this is pretty straightforward, just solve. So obviously the term in the front, square root v over r squared, that just cancels away, right? So you integrate 0 to get a constant, and then so dn dr is just that constant over r squared square root v. And remember, we have the right formula for square root v, right? It's v is 1 minus 2m over r. Okay, so we kind of lucked out here. So dn dr, we definitely know how to integrate that because, right, derivative of 1 over r is minus 1 over r squared. So integrating that, you see that it's just going to be a constant times square root of 1 minus 2m over r. Okay, well, plus a constant. So writing it in a more compact way, you see that n of r is some integration constant c1. So I absorbed the old capital C into this c1 times square root v plus some integration constant c2. So in other words, we've seen that if n is going to satisfy that Hessian equation, then n has to be of this form. Okay, but unfortunately, we can't stop there because we have to check that n actually solves the Hessian equation. And in fact, not every n of this form solves the Hessian equation. You can easily see that the constant c2 by itself does not, right? Because if you plug in n equals a constant, then its Hessian is 0, but n times Ricci is not 0. Okay. Well, you'd have to see that Ricci is not 0, but that's a computation. So the last step is finally you can check that this equation Hessian n equals n Ricci will be satisfied if and only if this n is if the c2 term is 0, basically. So if n is c1 times square root v. Okay, and then the final step, well, we may as well take c1 equals 1, because if you look at the original ansatz, right, you can just rescale t to make that constant go away. So in the end, we get this formula. Well, so we have basically, we know every spherically symmetric time independent solution of the vacuum Einstein equations has to look like. It has to look like this. And so we give this a name. This is the Schwarzschild metric of mass m. Okay, so now I can tell you why do we use the letter m and why do we call it the mass m? Well, now that we have the formula, right? What we could do is we can look at trajectories of particles, right? Of test particles that are, say, like, you know, have very large r, like they're very far out, you know, from the origin. Okay, and if you look at the trajectories of those test particles, they are very close to the trajectories of test particles that you'd see under classical Newtonian gravity. So this is kind of the reason why we can identify this quantity with mass, which is that the Schwarzschild metric of mass m, right, behaves just like a Newtonian point mass or Newtonian planet of mass m, at least near infinity. Okay, so the behavior, so the physics of this, right? It's not the same as the physics of Newtonian gravity, but as you go far away, it is most closely approximated by Newtonian gravity for mass m. So this is the reason why this is completely sensible to refer to this as a Schwarzschild metric of mass m. And in fact, as I said, this is the most reasonable model, or maybe the only reasonable model for what the physics should look like for, again, a spherically symmetric, unchanging object, at least outside of that object. Okay, so I just rewrote the formula here. So, but we're used to thinking of only positive objects with positive mass. So let's just think about the m greater than 0 situation here. When m is greater than 0, you can see that this defines a Lorentzian metric in the region r greater than 2m, and it becomes singular at r equals 2m, in the sense that when r equals 2m, right, you can see that the coefficients on dt squared and dr squared, they both become 0, right? So that's at that one point, that's not it's not a Lorentzian metric at all. It's degenerate, right? It's no good. But if you go past there and look at when r is between 0 and 2m, it becomes a Lorentzian metric again. except that the roles of dt and dr are kind of swapped, right? So when r is less, when r is less than 2m, the term 1 minus 2m over r actually becomes negative. So that means in this formula, the dt squared has a positive coefficient, the dr squared has a negative coefficient. So in that sense, right, the ddr direction is like time-like, and the ddt direction becomes space-like. So it kind of swaps that. But otherwise, it's a perfectly good Lorentzian metric. Also note that GM, this Schwarzschild metric, is asymptotic to the Minkowski metric as r goes to infinity, right? As r goes to infinity, right, the coefficients go to the 1 minus 2m over r approaches 1. And so this metric minus dt squared plus dr squared plus r squared d omega squared, that's just the Minkowski metric written in spherical coordinates. Okay, so now I want to try to find an alternate expression for the Schwarzschild metric. So what I'm going to do is we're going to solve for a new coordinate r star in this equation. Dr star equals 1 minus 2m over r to the minus 1 dr. This r star is usually called a tortoise coordinate in the literature, or sometimes called that. And the reason why I'm going to use this is we're going to define something called the ingoing Eddington-Finkelstein coordinate by the formula v equals t plus r star. And what we're going to do with that is we're going to trade in the t coordinate for the v coordinate, right? So right now our coordinates are t, r, and then some coordinates on the sphere, okay? And I'm going to switch that so then now it's v, r, and some coordinates on the sphere. So how do we write our metric in these new coordinates? Well, so here we have that t is equal to v minus r star, so dt equals dv minus dr star. So I wrote in red the one thing that's changed here. And it turns out, well, this is pretty easy to see, that this has this expression. So you can see that because in looking at the expression in red, if you do the dv squared, right, will give you that dv squared term in the new expression. And the cross term, right, the dv dr star, right? Well, if you looked at our definition of dr star, it's made so that it exactly will cancel out that 1 minus 2m over r. So you just get that nice dv dr cross term. But the really interesting part is that when you do dr star squared, right, that's chosen precisely to make the dr squared term disappear. So this kind of explains where the expression for dr star came from. We chose it precisely so that when we did this, the dr squared term would go away. So here's a different way of writing the same metric, just in different coordinates. But there's something really valuable that we can see here, is that this expression, unlike the previous one, is actually smooth across r equals 2m. And that demonstrates that the earlier singularity we saw at r equals 2m is just a coordinate singularity. It's not really there. It's just a manifestation of sort of having chosen like not good coordinates there. Right. I mean, simple example would be like when you write, spherical coordinates for r3, it looks like it's becoming singular at 0, but of course nothing's weird is actually happening at the origin. Okay, so maybe this isn't totally obvious, so it might be worth looking at this expression, right? This the formula for GM in these coordinates, and thinking about why it defines a Lorentzian metric at every point. So at the place where r equals 2m, you see the dv squared term will just go away, and you're left with 2 dv dr plus r squared d omega squared. But that guy's fine. That's a non-degenerate Lorentzian metric. If you can even find the orthogonal basis if you like. So anyway, so this is opens up a lot of interesting ideas. So, however, the same is not true as r goes to 0. As r goes to 0, the curvature actually does blow up. So it's not a matter of using of which coordinate you use. There's always going to be a problem as r goes to 0. This also shows you that if m is negative, right? Well, then you also are going to have the same curvature blow up as r goes to 0. Okay, well, I said it's not singular at r equals 2m, but something interesting does happen there. And you can again, just you could compute this, that all of the future causal directions starting at r equals 2m, they all point in the direction of non-increasing r, right? So remember, the future causal directions, future timelike, future null, those are the only directions that particles or objects can move. And none of them can move with increasing r. So the consequence is that any test particle at a point where r is less than or equal to 2m can never reach the region where r is greater than 2m. So I have a, and in fact, if you start at r less than 2m, it's eventually going to crash into the r equals 0 singularity. Like the point has to eventually end up there. Okay, so I have a little picture to end this today's lecture. So here's the formula at the top for the Schwarzschild metric in Eddington-Finkelstein coordinates, and here's a picture of this Schwarzschild spacetime, again with one dimension suppressed. I'll talk a little bit more about this picture next time. To make the picture kind of look right, so this is in RV coordinates that you're looking at, and sort of one of the spherical directions. But the v coordinate has been chosen so that the v equal constant lines are not horizontal in this picture. They're actually kind of slanted to make this kind of look right. But yeah, so for now, it's the yellow curves that I want to take interest in, which is that you see that there's a r equals 2m. If you're outside of r equals 2m, you can have light rays or null curves that kind of veer off towards the infinity. But if you're inside r equals 2m, which is like the part I've colored black here, then the curve has to sort of stay inside of there. Actually, I said that I've colored this black. This diagram is taken from an upcoming article with Lanxuan Huang, and she was kind enough to make this diagram, this figure for us. Anyway, that upcoming article will cover a lot of the material that's in these lectures, but on a kind of a more basic level, actually. So this series of lectures can be thought of as kind of maybe in between that and what's in a book I have on geometric relativity. Anyway, so we'll pick up from here next time, and I hope you will join me for that one as well.